Okay, so good evening, everyone. Welcome to today's lecture by Dr. Vivek Singh. Vivek is actually belong to the first batch of INO training school, which is called INO Graduate Training Program, which started in 2008. So he was the first student in this program. But before that, of course, he did his integrated master's in physics from IIT Kharagpur and then joined the PhD program, which is also jointly conducted, of course, by HBNI and INO. And this was in the year 2008. And he worked as part of his thesis, the development of cryogenics bolometer for neutrino-less double beta decay in the TIN 124 under Professor Vandana Nannal. And he graduated in 2014. And soon after that, he joined as a postdoctoral fellow in the Department of Physics, University of California at Berkeley, where he in fact led almost, he took a major responsibility to cure detector, which of course is being run at the Gran Sasso lab in Italy. And specific responsibilities have been on the cryogenics group. We also supervised the entire cryostat commissioning and its successful final tests and so on. And he was actually the on-site coordinator for this group. And he significantly contributed to analyzing the Curious data. And since last year, almost a year back, he is now, since then, is an assistant researcher in the same department in the same institute, which is the University of California at Berkeley. And there, of course, he is now interested with a much higher level of responsibilities. He is the lead investigator in developing technologies that can be used for next generation ultra low temperature detectors for particle physics, about which I'm sure today he is going to talk about. And he also leads the R&D efforts for large surface area, very large surface, in fact, more than 20 centimeters square, low temperature calorimeter detector to detect scintillation and Cherenkov photons. And he also is currently also leading design and testing and characterization of novel bilayer superconducting transition edge sensors, and using the superconducting quantum interface devices called SQUIDs. And as I said, he's kind of, I can say, an expert on cryogenic detectors, and so led to that is a cryogenic photomultiplier tube that can be used below 100 millikelvin to detect single photons. So these are all very specialized detector technologies, which are going to play a major role in all these experiments world over. So we can expect a very, very interesting and illuminating talk from Vivek. So can I request Vivek Singh to start his lecture?
Thank you, Satya, for such a generous introduction. I was told that this was more for general audience. I have prepared my talk as such. It's not too technical, so if there's experts in the audience, they might be disappointed with the talk. But again, this is mostly for the students and not for experts. So what I'm going to talk about is essentially the principles of the low temperature detectors and how we use it in certain applications in neutrino and particle physics. What I have done is I have selected few examples where we use low temperature detectors in neutrino and particle physics. And I will just tell you why the low temperature detectors play a significant role in those experiments. I'm not going to go over all the experiments that are being done. It's way too many to be listed down here. I'm also not going to compare it with any other experiment which uses a different detector technology. I think that's just unfair. They are marvelous in their own sense. Also, I'm not going to talk about the physics of neutrinos or the particle physics in general, but I will to motivate the physics behind the experiments before explaining why, again, the low temperature detectors will be useful for that. If you want to know more about neutrinos and particle physics or some of the other topics mentioned in this talk, please visit the excellent lectures from previous speakers. They are on the INO YouTube channel, the INO Outreach YouTube channel, and I went through a couple of them, and they were really interesting and pedagogical. So low temperature detectors, they have been extensively used in different fields. They have been really used in cosmology, in neutrino physics. They have been used for direct neutrino mass measurements, as well as in neutrinoless double beta decay experiments. We also use them for dark matter searches, not to mention a lot of applications in nuclear and atomic physics, material sciences, and now we are trying to figure out if we can also use it for upcoming quantum computing technologies. The idea is that no one size fits all. All of the applications over here, they have different sizes, different masses. It can go from micrometer to about a scale of centimeters, and it can be also made like as small as milligrams or micrograms to as big as, say, a ton size detector, like what you see here in Core. So again, depending on the application, one has to appropriately choose what kind of detector they want to make and how they want to design it. It's not something like a semiconductor detector, germanium detector, or silicon detector that can be. We haven't reached a stage that it can be actually made in an industrial setting. So most of the labs around the world actually make their own detectors and deploy it in the field. So what do detectors measure actually? So if there is a particle interacting inside a detector, the particles carry some energy, and when it attracts, some of the energy will be transformed to light, or it can also generate charge inside the crystal or the detector, and some amount of heat. And the whole idea is that all the experiments, they try to measure some combination of these channels. So the idea is to measure the energy of that incident particle. And you can do it by measuring the scintillation light or the charge inside the detector or whatever is left behind in the detector, which is essentially just heat. So, and heat is nothing but phonons inside a solid state detector. So people have been using various combination of it depending on the applications. In certain experiments, you'll find that a detector is actually measuring both charge and light. In some others, you can see it's being they are trying to measure both light and heat, and in some charge and heat. I haven't found a single application or instance where all three channels are measured together. And it's probably because it's really hard to find a material where you can measure all three channels together. So it's limitation. I think ideally it would be perfect if someone can measure like all three channels and get the total amount deposited very accurately. But I think that's a far goal right now. So what are the advantages of the low temperature detectors? The most um, significant advantage is essentially the resolution of the detector. We can measure energy very precisely using this heat detectors. And why is that? So the resolution actually depends on the number of energy carriers that we produce inside the detector. And for photons, if I have 1 keV of energy, then I will produce only few photons. Whereas for the same amount of energy, I'll produce in the charge channel, I will produce few hundred electrons. Whereas in the heat channel, because the excitation energy needed to generate a phonon is only milli-electron volts, we will produce about few thousand phonons, which means way more energy carriers in the phonon channels than, say, charge and scintillation channel. So that's why if we have to measure really tiny amount of energy and very precisely, then low temperature detectors definitely give us a handle on it, and that's the main advantage. Is it always good? Not really, because if you have an application where you really need good timing information, then the heat channel is not that great. So the phonons are nothing but carriers of sound inside a solid. So you can just estimate, like given the speed of sound in solid is kilometer per second, the best timing resolution that you can get is probably a microsecond or few tenths of microsecond. Whereas in charge channel, you can get up to nanosecond resolution, and in the light, you can get extremely fast signals to the resolution of picoseconds. So low temperature detectors, we have to choose and selectively apply it in applications where one needs very good energy resolution, but can get away with slower responses. So it's not something that we would be using, say, say at LHC or in an accelerator setting where there might be a lot of events and it cannot be resolved because of the timing issues. So one has to be careful that low temperature detectors are not always better because they have good energy resolution. So why low temperature physics, and why do we go to low temperature? Why not do this calorimeter measurement at room temperature? So if I just, for an example, if I just take a tin detector of 1 gram and I estimate what would be the temperature rise in it when a particle of 1 keV interacts, deposits all its energy inside the crystal, then you can see at 300 Kelvin, I get a temperature rise of 3.5 10 to the minus 14 Kelvin. Now this is a hopeless measurement for now. There is absolutely no way we can measure this tiny amount of temperature rise at 300 Kelvin. However, if we cool down the detector to say 10 millikelvin, then life is slightly easier. It is difficult. The temperature rise is only about 100 to 150 microkelvin, but it's possible to detect at least microkelvin temperatures in a certain way. So this is why we go down in temperature. The lower, the better. There's also another reason we go down lower in temperature. It's essentially there's a limit of how well these detectors can perform. And that limit in energy resolution is given by this expression. So since the heat capacity of the crystal, that's just the amount of heat that the crystal can store, uh, the energy resolution is dependent on the temperature of the crystal as well as the heat capacity of the crystal. So again, from this expression, you can see that if you really, really want to minimize the thermodynamic limit of the energy resolution, then we need to go way down in temperature. Okay. And what this means is that this requires operating these kind of detectors requires ultra low temperature facilities with ultra stable operating conditions. Because life is slightly harder as low temperature experimentalist. We cannot just, it's not something that we open the box in room temperature, quickly fix something and close it down. Getting these things cooled down takes a lot of time and effort. And as I will show later, like some of the experiments, you actually don't want to open up the cryostat after cooling it down. The resolution is actually not just determined by this quantity over here. It's also determined by the noise from the electronics and vibrations on the crystal, because vibration essentially is just phonons from outside worlds, like background phonons. So any kind of vibration will actually can mimic the signal inside the calorimeter. So again, the really difficult part in these kinds of experiment, apart from making the detector, is also to actually make a facility where you can have very low vibrations and really good electronics. Because uh, from the electronics, we can think about in terms of power, like even picowatt of power or femtowatt of powers, depending on the size of the crystal, can heat up the crystal. So we really do not want any tiny amount of power being dissipated on these detectors. Okay, so let's keep that in mind. So once we go down lower in temperature, it's all good. We create phonons, but then there should be a way to actually detect these phonons. These phonons, we don't actually read out the phonons by itself, right? So the phonons have to convert it in some channel so that we can finally, everything comes out to be everything has to come out as an electric signal that we can process and then get information from that. So there has to be a way to actually convert these phonons into electrical signals, and this is what the job of the sensor is. So there are the choice of the sensor technology is also always as crucial as the absorber that we choose for our detectors. And there are, I have shown here 3 kinds of thermistors. Essentially, In semiconductor thermistors, the resistance actually goes up as we go lower in temperature. And so the main benefit is that these are wide operating temperature sensors. There's a large temperature range where we can bias our sensor and try to detect that if there is a temperature rise, then the resistance changes, and we can measure that resistance change in terms of voltage. Yeah. We can also not just look at resistance, we can also have some paramagnetic sensor material where we measure the magnetization, which also depends on the temperature. So as the temperature changes, the magnetization changes, and we can measure out this magnetization. The semiconductor thermistors, they are fairly large size and they have high heat capacity. So they have a very slower time response. It's of the order of milliseconds. Whereas this metallic magnetic calorimeters, their time response is about 100 nanoseconds. They are pretty fast when compared to semiconductor thermistors. There's also another category of sensors, which are transition sensors. Essentially, they have it only has a superconducting film, and we bias the detector or the sensor, say at the midpoint of the critical midpoint of this transition. So it will have some normal resistance, and as it superconducts, it goes down to zero resistance. So we just put in some amount of heat and make sure that the detector is the detector resistance is somewhere here, and this has a very steep dependence on temperature. So if there is a tiny amount of temperature change, if the temperature goes up, then the resistance goes up, and we can measure this change. And in here also, because we are using superconducting metal films, metals have slightly higher heat capacity than than the other sensors shown here. But the benefit is that this can be made made in extremely small sizes, like of the order of micrometer by micrometer sizes. And because of that, the mass is small and the total heat capacity comes out to be smaller. So that's how we optimize the superconducting metal films, and we can get a time response of the order of microseconds. So this is, I'm just showing what a real detector looks like and how it operates. So essentially we have this huge crystal. It has to be connected to the thermal bath, which is being cooled down to 10 millikelvin or whatever the base temperature of the cryostat is. And then we have a sensor which reads out which converts this phonon energy into electrical signals. And the way it works is that initially, if there is a energy deposition inside the crystal, initially, like there's no temperature change, and as soon as the particle interacts, the heat will start building up, the temperature will start going up. But at the same time, some of the heat will be actually leaking out through the support materials, which in case of core is Teflon, right? So it's like filling a bucket of water, filling a bucket with water, but the bucket is leaking, right? So it will keep going up, and then at a certain point, it has deposited all its energy, and then the heat will actually start again leaking out from the detector. Okay, so this is what a pulse formation in a low temperature detectors looks like. Okay. And it is not necessary to actually always know the absolute temperature rise. Most of the times what we do is calibrate it against known energy sources. So I probably in particle physics, we actually don't care whether it's exactly 100 microkelvin or 150 microkelvin. It would be nice to actually know that, but it's difficult to do that. So what we do is actually calibrate this detector against known energy sources. And by looking at the pulse height, this amplitude of the pulse, we can determine how much energy was actually deposited inside the crystal when the particle interaction happened. So I guess that's clear over here. So why don't we go ahead and use some of this knowledge to detect some processes. So one of the things that people have been looking at is direct measurement of neutrino mass using low temperature calorimeters. There are other ways to do it, like Catherine has been doing with a huge spectrometer. But this is an interesting thought of using low temperature detectors to measure the neutrino mass. So here I will take a slight detour because I'm talking about neutrinos, so maybe I'll just introduce what the neutrino mass I'm talking about. So neutrinos are everywhere. They come from sun, reactor, atmosphere, and we can also produce it in accelerators. We know that there are 3 types of neutrinos. Why there are only 3 types of neutrinos, we don't know yet. And we also know that the neutrinos oscillate. So there are 3 flavors of neutrinos, and they oscillate among themselves. And this is only possible if they have mass. Okay, and this is a mass that is still not known to us. We want to precisely measure this mass. And what do we mean by oscillation here? So suppose we have this atmospheric neutrinos. Oh, this slide has not shown up correctly. Okay, I apologize for that. So essentially, I was trying to show you is that if I have certain probability of observing the mu type neutrino, then the probability changes as the mu type neutrino traverses through the atmosphere. And by the time it reaches the ICAL detector, for example, it could have just oscillated into a different flavor. Oscillated into a different flavor means that the probability of obtaining this new mu may not be 100%. It can be something else where that the remaining fraction could be any of the other flavors that you see here. Anyways, so the highlight was that this is possible only if they have mass, and that's why we are interested in measuring the mass of the neutrinos pretty accurately. That tells it will tell us a lot about the physics of the neutrinos. Okay, so one of the things, the way we can measure it is through single beta decay. Now, the single beta decay, a neutron can convert into a proton, an electron, and antineutrino, and this process is explained by the standard model. Okay, and lepton number over here that I show, it's essentially just like quantum number for a particle, like charge is a quantum number for a particle. Similarly, every particle can be assigned another quantum number, which is called lepton number, and it's 0 for neutrons and protons, and 1 for electrons, and -1 for antineutrino. So like charge, it is, I mean, we saw earlier it was believed that lepton number is also conserved, but that's kind of an accidental symmetry. There is no reason for it to be conserved like what we believe it should be for charge. Anyway, so so if I have to measure the energy of the electron and look at the spectrum of what the spectrum would look like for single beta decay, then you can see there will be continuous spectrum for the energy of the electron. And why is it continuous? Because some of the energy is been taken away by the neutrinos, which we can't detect because neutrinos are really hard to detect. If there were no neutrinos, then what we would see is essentially just a peak at the Q value of the reaction. But we observe this Q beta. Now, this is fine. This would have been fine if assume that the neutrino has 0 mass, then this would just end at a certain point. What happens if neutrino has mass? If neutrino has mass, and if we zoom in towards the endpoint of the spectra, then what we expect is that there will be this slight kink below the Q value of the reaction. And most of the experiments who look for this neutrino mass through direct measurements actually look for this change in the shape of the spectrum near the Q value. Okay? And the idea is that we need to minimize the number of electrons in this region. And this depends on the Q value of the reaction. So the lower the Q value, the less number of electrons that can be in here, and that's better. So that's why people who look for this single beta decay, look for this neutrino mass through single beta decay experiments, essentially go for isotopes that have a very low Q value. Okay? And the experimental challenge is, again, because it's such a tiny amount of energy difference, you want to have a good energy resolution. So the low temperature detectors satisfy this criteria. We should have enough number of decaying atoms so that we can get good enough statistics to actually discern between those two spectrums. However, it's not always good to have a large number of candidate events, because then we also need to resolve events that happen close to each other temporarily, right? So if there's pile up, if there are too many events, then the second event might come before the first event's heat has leaked out completely. So there can be pile up, and that's one of the main issues for this low temperature detectors. So for that, we need good timing resolution, and we know that low temperature detectors do not always give good timing resolution. Okay, so these two needs to be optimized. Okay, the experimental runtime also needs to be in years, because these are extremely we are talking about very small statistics here. Sorry, we are talking about taking statistics for a very large amount of time. So if you set up an experiment, you have to make sure that it runs for 4 years or 5 years for good statistics. Which means that if you have set up a facility for low temperature, then that facility has to continuously run for 4 or 5 years. And it is extremely difficult to find a candidate element that satisfies most of this criteria, if not all. And that has been a problem for low temperature detectors for these measurements. There have been significant. So do you mind if I just stop here and switch over to my, actually, let me share my keynote presentation. I think a lot of things are not showing up.
It's not showing up, right?
Yeah, a lot of stuff is not showing up. So I don't want that. All right, can you see it?
Yes, you can.
Okay. But you can't see the pointer now?
Yes, we can't see.
Okay. Hold on. Let me see. All right. Do you mind if I go in like this? It might be better. Yeah.
That's fine.
Yeah.
We want to enjoy your animations anyway. Oh.
Yeah. So there have been efforts to actually measure this using low temperature detector. Initially, most of this were started in Italy. The first effort was on rhenium, and you can see here there's a tiny amount of rhenium crystals coupled with a germanium entity sensor, and people tried to measure the spectra. They actually did measure a spectra and put a limit on the mass of the electron type neutrino. Then also there was another experiment, MeBeta experiment, also looking at rhenium, but this time using different crystals, like a compound of rhenium instead of just metallic rhenium. Okay, the metallic rhenium had a problem. It was seen that most of the energy deposited in here was not actually converted into phonons. It was going in some other channel, and people actually didn't understand why 95% of the signal is lost in some other channel. So there's some superconducting physics inside here, or how the energy thermalizes inside a superconductor that needs to be studied. And people didn't have a great success with just superconducting rhenium. So they changed the crystal. They found the compound with rhenium in it and tried to do an experiment. And they again tried to measure the spectrum. They did and put a better limit than the Manu experiment. And this effort of trying to use rhenium actually went on for 16 years. Okay, and this shows I have put in this example just to show how difficult it is to actually make low temperature detectors. So even after 16 years, they had to actually drop rhenium for now, because they were not able to find a suitable compound or suitable detector absorber, which includes rhenium, which can give a which can satisfy all the criteria in terms of energy resolution as well as timing resolution. Yeah. So recently, there have been some other efforts where there's another way to look at the neutrino mass. This is not through beta decay, but through electron capture, where the nucleus actually captures electrons from the orbit of the atom and emits a neutrino. And again, the detection principle is same. So there will be spectra, and there's an endpoint here, and there will be some change at the endpoint of the spectrum that people plan to measure. Okay, and this electron capture candidate is for 163 holmium, and the Q value is low, so that satisfies it. And people are trying to actually implant holmium ions in a substrate, a certain number of holmium atoms on a substrate, on which they will attach the transition edge sensors and try to measure the temperature rise and measure the spectrum. So these are the recent efforts in trying to measure the neutrino mass using low temperature detectors. I have put in the references so that you know what to look for. If as a student you are interested in, you can go and visit this. They have wonderful websites with a lot more details than being shown here. So it's a pretty good idea on how to do measurement, these kind of measurements. So that's on single beta decay. Where the low temperature detectors have really found an use is for neutrinoless double beta decay. And essentially, this is actually proving if the neutrino is its own antiparticle. Okay, so let's revisit the beta decay again. So in certain nucleus, we have this kind of schematic where a nucleus cannot undergo single beta decay because it's energetically forbidden. However, there's a second order process through which the candidate nuclei can undergo double beta decay and emit 2 electrons and 2 antineutrinos in the process. So the single beta decay and this double beta decay, they are both explained by the standard model. Okay? But however, if neutrinos and antineutrinos are the same particle, there's a probability that actually it will be emitted from one of the nucleons and get absorbed by another nucleon. And for that to happen, the neutrino and antineutrino have to be the same particle. And in that case, no neutrino comes out because it has been absorbed internally, and only 2 electrons comes out. Okay, and this process is hypothetical. It's not explained by standard model, and this is also only possible if neutrinos have mass. And in this case, the lepton number is not conserved. Okay. So there's a lot of physics motivation in trying to look for this process. Apart from like non-conservation of lepton number and probing the neutrino mass, this process can probably also explain why we have more matter in our universe than antimatter. So suppose in the early universe, where after the Big Bang, there should have been same number of particles and antiparticles created. So leave aside this blob over here. But after a certain point, there must have been some asymmetry that created more matter in the universe that we see, and radiation all around it. And how do we know actually that there's more matter in the universe? We can do a simple calculation. We know the number of photons in the universe. That's about 400 photons per centimeter cube. And we can have a rough estimate of how many baryons. So baryons essentially is the matter that we talk about, protons, neutrons, and other baryons. How many baryons are there? And this is a simple calculation for students, and that's why I have put it in here. So there are in a star, there are probably about 10 to the power 57 nucleons, and then you can estimate how many stars are there in a galaxy, and an estimate of how many galaxies are there, and you can calculate out what is the total number of baryons. So if you look at the ratio of number of baryons over number of the radiation, the gamma radiation, then it comes out to be 10 to the minus 9. Okay? And if there was no matter antimatter symmetry, then it would have been just 0, right? So everything should have been just radiation. So we believe that neutrinos, heavy neutrinos, actually hold the key in explaining on how this reaction took place early in the universe that created this extra extra mass or extra matter in the early universe. And for that, I mean, one of the things one can easily see is that it has to be a neutral particle, right? If charge is conserved, then there's no way a charged particle can do this kind of can create this matter-antimatter asymmetry. So neutrinos are neutral fermions, and maybe they hold the key in explaining this asymmetry. So that's so I don't know how many of you are Marvel Comics fan. I found this very amusing when I was watching the movie, that the main antagonist of the movie actually said perfectly balanced as all things should be, when in nature we clearly know that it is not. If they were all balanced, then we would not be here. We would be just radiation. But we know that we have more matter in the universe. So coming back to double beta decay and how exactly we can probe the Majorana nature, or the fact that neutrinos are their own antiparticles. So let's go back to looking at the spectrum. We have 2 neutrinos decaying to 2 protons and 2 electrons with 2 neutrinos. Again, if I just look at the total lepton number, then this is 0, explained by the standard model. And if I plot the sum energy of those 2 electrons, then I'll see a spectra, which is just like the single beta decay spectrum, because the other, like it's not a delta peak at the Q value, because some of the energy is actually taken away by the neutrinos that's coming out. However, if they are Majorana particles and no neutrinos come out, then we will see this peak at the Q value of the reaction. And in this case, again, you can see the lepton number, there's a change of lepton number, and the lepton number is not conserved. And this process, I have written it wrongly over here. This is not explained by the standard model. So this is what we are trying to look for, tiny peak at the Q value. Yeah. And if I have to summarize, this is the experimental signature. So I have a continuous spectrum of 2 new beta beta, and at the end, I'm looking for this tiny peak. We even don't know whether this will happen or not. And even if it happens, its rate is really, really small. So that rate can be defined in terms of half-life of this experiment. And that half-life depends on the mass of the isotope that we're using to probe, the lifetime of the experiment, the background near this peak, and also the energy resolution. So obviously, if you want to have a very good energy resolution, if you want to discriminate this peak from the background in the energy of region, then we need to have detectors with very good energy resolution. So low temperature detectors fit this bill. Okay? And also we can make massive low temperature detectors, so we can increase the size here. So mass is pretty long. It's difficult to actually get these two things right. Like having a cryogenic facility run for 5 or 10 years is hard. And also the background for low temperature detectors is not, the background rejection for low temperature detectors is not as great as, say, some of the noble gas detectors. Yeah? But there are efforts to actually improve on this background. So how do we minimize the background? How do we keep this term low? So we go under a mountain, we cut the cosmic background, and then we clean. We just keep cleaning everything around the detector, so that nothing from the vicinity of the detectors or nothing from inside the detector can give us background counts in the region of interest. Yeah? And in a way, everything contains small amount of radioactivity around us. Okay, even like if you're doing an experiment, if you're setting an experiment for double beta decay, even a drop of tear, blood, or you're working hard and you're sweating, and a tiny drop of sweat goes and hits a detector, your whole detector, your experiment is ruined. So all of these things are done in a clean room, in a very special environment, to make sure that they don't see any radioactivity. Okay. And the longest lived naturally occurring background sources, they have a half-life of 10 to the power 7, 10 to the power 9 years. Whereas for neutrinos double beta decay, the half-lives is way more than 10 to the power 24 into 10 to the power 25 years. So what this means is that the expected rate is very small. And this is perfect for large low temperature detectors, because we then don't have to worry about pileups like what we did for single beta decays. Okay, so the rate being smaller, we can just let the detector run without worrying about the pileup effect, unless the pileup is coming from this process itself. So you can imagine there's two new beta beta, two new beta beta happening at the same time, and if they are close to each other, then they can mimic the signal at the Q value. So one has to actually reject the pileup from the two new beta beta itself, but the main candidate process will not give any kind of pileup. So how do we go about probing this? There are only a handful of candidates that can undergo double beta decay. And I have just highlighted some of the candidates where people have been either thinking of making a volumetric experiment, or there have been efforts to, Core is already running a ton size experiment looking for double beta neutrinoless double beta decay in 130 tellurium. Cupid is going to be an upgrade on Core, and as a baseline, it's going to look into the double beta, like neutronless double beta decay in 100 molybdenum. And I initially, like for 5 or 6 years of my life in TFI as a grad student, I was working to make the STIN detectors. It's an initiative for INO. And hopefully if INO sees light at the end of the tunnel, we can have the double beta decay experiment in India also. I have not highlighted other isotopes in here. Germanium, xenon, these two. Germanium uses a like Gerda or Legend. They use a semiconductor detector made out of germanium. They're one of the leading experiments in the field. So is Nexo. They have also tried to measure neutrinoless double beta decay and 136 xenon, but they use different detector technology. So there are different ways to go about it, and it's important to actually probe as many nuclei candidates as possible to make sure that physics should be same for all the candidate nucleus. So if we see neutrinoless double beta decay in one isotope, then we should see it in other isotopes too, and that will reduce the systematics and give a more insight into the physics of physics beyond standard model. So, so this is what I had worked as an undergrad student. So this is Tintin experiment at INO. We had set up a lab at TFR, which can go inside a cavern whenever we have an underground lab. And we had some initial testing with tin over here. So we are planning to use tin, which can also undergo double beta decay, as shown in the previous slide. At the surface, we can only test out small detectors because the cosmic rays will give a large number of events inside that at the surface. So once you go inside a cavern, then you can go for a larger detector size and maybe scale it up to even kilograms or tens of kilograms, or maybe who knows, even hundreds of kilograms. One of the things that's good about this detection technique is that it's easy to scale up. You can make detectors out of most of the things have some should I say, some compound which does not have a high heat capacity. So you can select a compound which will have extremely low heat capacity at low temperature and try to make a detector out of this. Whereas a semiconductor detector, you necessarily have to make something that's semiconducting, right? So that is a band gap. So low temperature detectors offers a lot of flexibility when it comes to making detectors for different nuclei. And you can make the source and the detectors the same because the electrons that's coming out after the decay, they have a very short mean free path. So they are not. So if it's happening at the center of the crystal, the electrons are not going to come out, which ensures that all the energy is actually deposited inside the bulk of the crystal. So you can make this bigger and bigger, and it will probably contain all the events that's going to occur inside the detector. There's a negative point of it is that it's not background free. Anything that comes and hit this massive detector, it's hard to tell whether it's from the electrons from inside the crystal or from something from outside the crystals. So that's another thing that we actually worry about. Just to show what's the state of the art, Core is a ton-scale experiment currently running in Italy. They have an underground lab under the mountains, and Core is running in one of the halls in the Gran Sasso National Lab. It has 988 detectors, and it's being operated close to about 10 millikelvin. It's already been about 3.5 years since it's taking data, and it has put some of the best limits for the rate of neutrinos double beta decay. This is what actually the detector crystals look like. Excuse me. This you can see there's towers, and each crystal is like a brick. So with each floor has like 4 of these bricks, and then we make the tower brick by brick, layer by layer, and then one tower has about 52 crystals, and we have 19 of them. To again give an idea of how difficult this is, it takes about a month or 2 to actually cool it down to 10 millikelvin from room temperature. And if we have to warm up, it will need another month or 2 to warm the whole system up. So thankfully, we haven't done that a lot. Just once we had to warm it up only once. And we are not even thinking of warming it up again. The experiments needs to run for 5 years or more than that, and we want to collect as much data as possible. So how to improve on Core actually? So as I said, right now Core only measures the thermal signal. There is no way to tell whether the event came from outside or from inside the crystal. And one of the limiting background is the alpha particles from the nearby surfaces. Okay? So the alphas will actually come from nearby surfaces, lose some of its energy inside the surface of, say, copper, and deposit the rest inside the tellurium dioxide crystals. And it is a major source of background. So there has to be a way to actually reject these alphas. And the idea is actually to use scintillating crystals and read out both phonons and photons that come out from these crystals. Okay, so tellurium dioxide is not scintillating. That's why we have been trying to move towards 100 molybdenum, because you can make a scintillating bolometer for molybdenum. And in there, the idea is that the amount of light produced by alpha will be significantly different from the amount of light produced for betas. So we can actually reject by looking at the yield of heat and light together. We can reject the alpha particle and get a better background. This has been recently demonstrated in an experiment called Cupid molybdenum, which uses lithium molybdenum crystal. So in here you see this is a large size lithium molybdenum crystal. And then on top of that, we have put another auxiliary crystal that's also auxiliary crystals that detects the light coming out from this main crystal. Okay, and this auxiliary crystal is nothing but a germanium wafer using NTD sensor, and the detection principle is same. In this case, it's mostly interested in detecting the light coming out of this crystal. And how do we actually differentiate it? So if you look at the light signal against the heat signal, then you can see that the alphas have noticeably a different slope than what you see for electron and gamma like events. Okay? So this is a nice handy tool to actually remove alpha events from the spectrum, alpha like events, and reduce the background further. And this is what we are trying to do for Cupid. Okay. Now, there is a lot of optimization that needs to be done for this auxiliary detector. And this is another thing that I have been working on personally. And I'm working on this large area large surface area light detectors, but with transition edge sensors. Okay, and why transition edge sensors? Because they are fast, at least faster than the NTD germanium sensors, and we need to speed it up because there's a concern that there will be some pileup from the 2 neutrino beta beta spectrum at the Q value. Okay, so that's why we are trying to make these detectors. We have got some good results, at least from the point of view of timing resolution. We have achieved something like microseconds, 20 microseconds, and this is more than enough for our application. Okay. What we need to show is that we need at least an energy resolution of 20 electron volts or 20 to 50 electron volts to actually detect the light coming out of the crystal. So the challenge is to have small timing resolution as well as very low threshold and good energy resolution. So that's what people are trying to do. So that's for single beta decay and neutrino stable beta decay. There's another process that we can use to study neutrinos and use neutrinos to actually use them as a nuclear probe, and that's coherent neutrino scattering. So what's coherent neutrino scattering? In this case, the neutrino comes in, and for a small momentum transfer, it recoils against the nucleus. And in this case, the nucleus recoils as a whole. It's not that the neutrino will come and interact with just one of the nucleons, like proton or neutron, then recoil. In this case, it recoils as a whole, and that has a larger, and that's what we want to see with neutrinos as a probe of the nucleus. Okay. This is a standard model process. We understand this, and it has been observed. However, we need more experiments and with more precision at lower energy to understand the fundamental interaction of this neutrino with the nucleus. Okay. And since the momentum transfer is really small, we are talking about detectors which should have a threshold of, say, 100 electron volts or something of that order, which means extremely low energy, and that's where low temperature detectors comes into play, because you can make it small enough, or you can tune it to have a really small threshold and good energy resolution. So there's an experiment called Ricochet, which is trying to make first detection of coherent neutrino scattering from nuclear reactors. So that would be a first from a nuclear reactors. And they are using zinc crystals coupled with transition edge sensors to observe this observe neutrinos from the reactors. So that's another thing. This process can actually be also used for reactor monitoring, apart from actually looking for new physics beyond standard model. So far for neutrinos, that's the few topics that I had picked from neutrino physics. Low temperature detectors have also, in particle physics, have mostly found use in dark matter searches. And let's just see what the evidence for dark matter is. And again, this is not for experts, but I find these two evidences. There are a lot of evidences that tells us that there should be dark matter in the universe, but these two images really fascinates me. The first one actually shows if in a spiraling galaxy, if you look at the rotational speed at a distance from the center of the galaxy, then you should expect that the rotational speed should come down as you go further and further away from the center of the galaxy. However, we see that it does not. It kind of flattens out after a certain point, and which tells us that apart from this visible matter, there is something else that is actually holding up or actually making the galaxies massive. And that's what we call as dark matter, because we exactly don't know what they are and what their mass is, what their properties is, but we know that they are massive. Yeah, and this is another picture which clearly shows it's a spectacular picture to show like the dark matter. So what you see here in white and yellow, these are say uh, galaxy clusters, and sorry, these are stars and visible matter, and you see two clusters actually colliding with each other. Okay, so the thing is, this blue over here, this is where we have observed that the mass of this colliding cluster is located, whereas the visible mass is somewhere around here, that's shown in red, right? So it shows that the actual mass is concentrated somewhere else than the visible matter. Okay, and that's probably because of dark matter. So how much dark matter do we have in the universe? We expect about, like, the matter as we see, and there's only 5% of it, and 25% of it is dark matter, and the rest is dark energy, which again, we have no idea what that is. So people have been trying to first figure out like if we can do a direct detection of dark matter. And the way we try to do it is that we expect, since our Earth goes around the orbit, it will hit some weakly interacting massive particle, and if that is observed in our detector, then we can try to study that. Yeah. So there's experiment called Super CDMS, which actually uses detectors that employ both charge and heat detection for the detectors. It looks something similar to Core, but it is not. So there are a lot of electrodes plated on the surface of the detector, and it's also equipped with transition edge sensor to read out the heat channel. Okay, and what do we gain? What do they gain by reading both of this out? They certainly can measure tiny energy deposit, but they can also, this ionization channel also helps discriminate the electron recoil from the nuclear recoil. So this electron recoil is mostly come from background events, and the nuclear, because this is massive particle, so the nuclear recoil will come from the candidate events. Right? So this is how we try to do that. The initial payload for Super CDMS will be something like 30 kilograms, and maybe in future they will scale it up to 200 kilograms. Super CDMS is actually, I mean, before this there was CDMS, where they had some success, and they were the leading experiment for this weakly interacting massive particles using low temperature detectors. There have been much more significant efforts in Europe also. So this CREST experiment, and this is in Gran Sasso, and Edelweiss is in France. And they also use different materials, different candidate nucleus on which the weakly interacting massive particles can interact and deposit energy. And the detection principle is slightly, at least for the CREST, is slightly dissimilar to Super CDMS, but this is very similar to what Cupid will try to do. So you can see there's a lot of synergy between different experiments, even if they are trying to look for different processes. So for CREST, they use a calcium tungsten crystals with scintillates, and this helps them reduce the background coming from other events. So they look for the heat channel and the light channel. For Edelweiss, it's more like similar principle to that of Super CDMS, so where they measure both the ionization channel as well as the heat channel. However, they don't use transition edge sensors, they use NTD germanium sensors for detecting this. So in India also, talking about INO, there's an initiative to actually do dark matter detection at INO also, and the experiment, I actually don't know whether it's still considered, but there's actually proposal to use scintillating crystals in the ionic cavern to actually look for this dark matter detection, and the detection principle will be very similar to what CREST is doing, or what Cupid will do for neutrino low stable beta decay. And hopefully this also, like Tintin, can go inside the cavern someday. This is slightly off the topic, but there is quantum information science, or quantum computing is an upcoming field. You must have heard about quantum computation with qubits. And there's a lot of synergy with low temperature detectors in this field also, especially for high energy physics, because we also, in high energy physics, we also try to read out multiple channels. We try to do multiple multiplexing. We try to minimize noise, make the noise closer to the quantum limit. And these all are the characteristics that also is needed in quantum computing sector. Okay, so especially if there's an implementation of quantum computer in using superconducting electronic circuits, then we can share knowledge about the readouts and the quantum sensors that can be probably used in high energy physics to explore new physics or to make novel experiments, not just for so people are actually trying to see if we can use this quantum sensors to actually use it for dark matter experiments or not, or look for other particles like axions or not. And we are also looking at possibility of using some of the techniques that have been used in quantum information science to effectively increase our readout, like increase our number of channels that we can read out from us from inside the cryostat. So currently, state of art, like in cosmology, CMB detectors of 10, like Socore has about 1,000 detectors, and for cosmology experiments, they have successfully read out about 10,000 of detectors, low temperature detectors, and people are actually trying to scale up this number. And there are some ideas that maybe using quantum sensors, we can, techniques from quantum sensors, we can increase this to like 30,000 or even 50,000 channels. Okay, so there's a lot of synergy and a lot to be gained by collaborating with our colleagues in quantum information science. So I think that's the end of my talk. Just to recap, low temperature detectors have been really crucial and still are crucial for astronomy and cosmology experiments. It has played a significant role in neutrino physics, especially in the field of neutrinos Dolby decay, and it's trying to catch up with other experiments that measure coherent scattering of neutrinos or direct mass measurements of neutrinos. It certainly is a leading detected technology for dark matter searches, and it has also found wide-scale representation in nuclear and atomic physics also. As I said before, there is no ideal absorber for low temperature detectors. Everything has to be designed and tuned according to the experiment at hand. And there's a lot of mixture. Like if you're working with superconducting absorbers, you need to understand superconductivity and low temperature physics. And it's an amalgamation of different kind of physics going in there. So it's a pretty exciting field to be a part of. And hopefully, if nature is kind enough, then we can probably detect some of these exotic processes or beyond standard model processes using these high precision detectors. So we do have some exciting times ahead for low temperature detectors. I would say it's starting of new era for low temperature detectors. And I think that's it from me.
Okay, Vivek, indeed, as you said at the end, it's a very exciting field, which is, I think, full of opportunities, but also we noticed the kind of type of challenges that required to be overcome in order to, of course, achieve what you are saying. And particularly the way you describe the entire field of low temperature sensors and detectors, and also the applications wide, starting from astronomy, cosmology, but the particular applications in the neutrino, dark matter, and it's very interesting also to see the synergy between quantum computation, quantum information systems and energy. That's very nice that you brought this synergy. And I mean, I can't thank enough to you that you essentially stayed overnight to be able to catch up with this cruel timing, which was kind of forced upon you, working across the globe. But okay, so it's not yet over. It's only just to thank. But let me now invite the participants with their questions. And I hope there will be some amount of discussion that can go ahead, especially from the younger audience. Yeah, so the talk is open for questions, please. Let me start with a question from Balasubramaniam, KM. Okay, Bala, you can ask your question.
Okay, hello, am I audible?
Yeah.
Okay, so why is it always we are talking about double beta decay? I mean, why not about triple or quadruple beta decays? Is there any specific reason for double beta decay and neutronless double beta decay?
Yeah, you can have quadruple beta decay. The problem is you can see the half-life. It's already hard to detect a process that has a half-life more than 10 to the power 26 years. As you go higher up in order, the half-life will be much more than this. Right? So it becomes harder and harder. So the rate will be really, really small. And to get a background level to actually measure those will be really difficult. So one step at a time. If we detect this, then we can definitely think of measuring the higher order beta decays.
Okay, thank you.
Okay.
Can I just make a comment? I think Professor Rath in the 2016 NDBD school presented the rate for quadruple double beta decay. It was, quadruple beta decay. It was obscurely large. I think it was 10 power 64 years or something. I am not 100% sure, maybe 46 or 64, but it was obscurely large.
Okay, that's nice. Let us
maybe I shall take the reference of the paper from Professor Vandana Anand.
I don't think it's a published work. He had just presented it in one of the seminars. I'll see if there is a reference. Yeah.
Okay.
Yeah, there is a published work also. I mean, if you just Google quadruple beta decay.
Okay. Yeah, maybe. Okay, Rath probably wrote it for symposium. I'm not sure. Yeah.
Okay, thank you.
I thought Acharya had a question. Acharya?
Yes, I have a question.
Yeah, please go ahead.
Regarding this temperature, rise and the decay of this temperature. Okay, this microkelvin, how is that rise is so fast, which I am little difficult to understand. That is, it is a bulk temperature you are measuring, no? When you are cooling, it is taking much time, and it is the temperature which has increased, and it takes some kind of microseconds decay time. But how is that rise time becomes so fast? And is it dependent upon the volume of the detector, or where the interaction has taken place within the detector, whether deep inside or near the surface, like that?
Yeah. So that's a very good question. So what essentially happens, the rise time that you see here, at least for the Core detector, it's something of the order of 50 to 60 milliseconds. So it's not that fast. And you can see here in Core, it's the decay time is like large. I mean, this is a 10-second window. However, as I said, like this depends on the heat capacity of the crystal and also how the phonons thermalize. So in a thermal detector, if there's a particle interaction happening, we excite a lot of phonons. And there can be ballistic phonons, which will be really, really fast. But what we mostly observe here is when the phonons are thermalized. So we are looking at thermal phonons that they have like smaller energy, and they take a longer time to thermalize. And that's why if we are looking for thermal phonons, then the detector response is slower. if someone makes a detector like some of the people have been trying to make detectors which detect ballistic phonons, they are really, really fast. They can actually go down below microseconds, like detecting those fast phonons.
Yeah.
So
Thank you.
yes, it depends. The thermalization also depends on where the particle interaction happens. But at this time scale, it probably does not matter because everything has thermalized. But if you're looking for ballistic phonons, then there might be some dependence on the location of the interaction.
Yeah,
There will
I
be
have that. Okay, I have a related question. That is, you are continuously maintaining the detector at the 10 millikelvin or that. Okay, you are continuously maintaining it. So when it gets heated up, it may not be really reaching to the peak, no, because you are also trying to cool it.
Right. So that's what I referenced when I meant like it's like a leaking bucket, right? So
Yeah.
I'm trying to fill water, but some of it is leaking out, and at a certain time I stop filling water, and then it starts slowly leaking out from the hole. So that's what's going to happen here. So again, I mean, it does come back over a longer duration. So it comes back to the baseline. And even if it does not, then there are ways to actually thermalize the detectors and make it shorter.
Yeah. Okay.
Make the time duration shorter. It depends on the sensors also. So for example, not for entities, but transition edge sensors, we can have some kind of electrothermal feedback that can actually shorten the duration of the pulse. So it makes it come down to its baseline. Yeah.
Yeah. Okay. Thank you.
Okay. Professor Datar has a question.
Can you hear me? I've unmuted my microphone.
Yes, I can hear you.
So I have a small comment, but also a question. The comment is just about the measurement of mass using these, calorimeters, the rhenium calorimeter, the whole beam calorimeter. I think while it is an admirable effort, but I think the Catherine will get there if the mass is, reasonably large. But I think the future is actually in Project 8, where you measure the Bremsstrahlung from electrons. That has a sensitivity, ultimate sensitivity. I think the goal is about 40 millielectron volts. Right. But in the shorter term, they will have a sensitivity which is about maybe something like 2 to 400 millielectron volts, which is comparable to Catherine. That's just a comment. Yeah. So the only advantage, of course, of the Holmium detector is that you are measuring the mass of the neutrino as opposed to the anti-neutrino measurement in the case of tritium or rhenium.
Right.
Okay. The question is the following: that what is the ultimate resolution that these low temperature detectors, perhaps in much smaller sizes, have got? Are you anywhere close to the limit that the physics limit?
No, nowhere close to that.
So it is still dominated by noise sources.
It's still mostly dominated. We have not reached the quantum limit for this.
In any other detectors as well, right? Smaller.
In very, very small detectors, they have been shown in extremely good conditions in NIST to be reaching that limit, like say 0.5 electron volt resolution, but not below that. I mean, still there's some excess noise in this kind of detectors that comes from like electronics or maybe thermalization also.
Thank you.
Yeah, and my comment about like Catherine and Project 8, like again, those are like really good ideas, and I think they have more. I would say they might reach the sensitivity level faster than low temperature detectors. But since I was covering low temperature detectors, I thought I would just put it out there in case someone has a bright idea of making something out of this.
Yeah.
Okay. We will take, we still have quite a few questions, Vivek, maybe another 4 or 5. Let us go first to Aparajita.
Hi Vivek, thanks for a very nice. Am I audible?
Yeah, I can hear you.
Yeah. So I hope this is not a silly question, but I wanted to ask about the pile-up of the two new beta-beta background. How significant would it be? I mean, if I'm understanding correctly, two events would have to come in during the decay of the pulse, right? And since two new beta-beta itself is a very rare process,
Right.
I'm just wondering how it compares to other sources of background.
Yeah, so the thing with molybdenum is that molybdenum is the half-life of molybdenum itself is smaller than the half-life of, say, other, sorry, let me rephrase it. The two new beta-beta decay half-life for 100 molybdenum is smaller than, say, germanium or xenon. Okay, so we're looking at half-life of 10 to the power 18 years. Yeah. And if you're trying to measure a half-life of 10 to the power 26 years, then this becomes a cause of concern.
Okay. Okay.
Yeah. So there is a small but finite probability that it can mimic a signal at the Q value. Again, I mean, that won't be a problem if we have a fast enough detector that can just, the thermal signal might be slower, but we are also reading out the light channel. So if we can just tag on the light channel a very fast, which has a very fast time response, then we might be able to get rid of pileups, even the two new beta-beta pilots.
Thanks. Thank you.
Okay, we now go to Raj Pillai, Professor Pillay's question. Sir, please ask your question.
Yeah, Vivek, nice talk. There was this view graph which you had shown regarding those alpha contamination, surface contamination. That's right. Okay.
Yeah.
Now, if I look at the heat signal, the alpha is miles away from the electron signals. So I don't gain anything by having that dual channel.
No, you can see there are some dots over here.
So there's some red bit there also.
Yeah. So the thing here is this is statistics from the polonium peak, which is a main alpha background in the detector, and then there are these degraded alphas from the nearby surface.
So that was not visible to me, but then it's significant in this simulation.
Now you can see.
Okay. So,
yeah.
No, because it struck me that you're not it's not paying in doing anything because the alpha is going to be very high energy compared to the
so
gamma.
If it deposits all the energy in the crystal, then that's fine. It will reconstruct at a very high energy. The problem is a significant amount is lost in the, say, copper, and a tiny amount comes and hits the crystal. And
so when people have done it in this super CDMS and so on, for example, how much do they expect that cleanup to be compared to what they were doing just as a single detector? And if they do this dual combination? Is it order of magnitude improvement in background, or is it just
so I don't know about
a wee bit here and there?
No, so I don't know about super CDMS as it is, because it's a different
so in your qubit, for example, suppose you did
only but for core, the background level that we have is right now 10 to the minus 2 counts per kg per kV per year, and we are trying to improve that to 10 to the minus 4.
So you're trying to do 2 orders of magnitude better.
2 orders of magnitude, yeah.
And so you think that that's all entirely due to surface contaminants, which can be distinguished.
So we have background model where we fit the background model, and we see that most, at least right now for Code, the major contamination is from alphas from the nearby surfaces.
Now, I thought that if it is due to the general muon background and other things which are sitting underground, then that's not going to go away by doing this double.
Yeah, so that's why when we go to 10 to the minus 4, 10 to the minus 5, then we actually have to think about the muon background. So right now we are not there yet. So maybe in the next, like for Cupid, muon background might be a problem. Right now we are getting away by not putting in a muon veto. Maybe for Cupid, if you want to reach a very like good background of 10 to minus 5, then we'll need to actually put muon veto all around the grad start.
So for Cupid, you expect it to be maybe 10 to 100 times better than what you expect in Q, what you're achieving in Q.
Yeah, for Cupid, the goal is 10 to minus 4 counts. Actually, I don't have the slides, but it's point.
Okay.
The aim is 0.1 counts per ton per kVA.
How about the germanium wafer itself? That is radioactively very pure when you put such a large area.
Yes, so that's one of the concerns. This actually comes up in all the conferences. Because we are putting in this light detector, there is a concern that we are adding in extra material and there might be gamma background from this extra material or even for the sensors. So we estimate the like germanium and silicon, they can be made extra pure. They have been made for experiments like Legend also, and they are pure. So we don't expect a lot of background from the germanium itself. And also because the sensors are so tiny, we don't expect a lot of gamma background from the sensors. So the background projected for Cupid, I think we should be fine by using these crystals. But again, there's a lot of effort in simulating these detectors, simulating the background for these detectors in different geometry for Cupid. And
this transition edge sensor which you use, for example, for testing all these things, which you are using, okay, how wide is this width of the transition, and when you make this thin film on different times, do you get a very great reproducibility?
So what I have been using, we have been trying to make bilayer transition edge sensors, and making bilayer reproducibility is good. Like we can do it like deposit different metal film thicknesses pretty accurately on the surface. As for the transition is very narrow. It's only about 1 to 2 millikelvin at 30, 40 millikelvin. The point is we can actually shift this transition by applying current through the resistor. So this is at a certain bias current. We can always increase the bias current, heat up the transition sensor, and shift it at lower temperature. So even though the actual transition temperature is say 40 millikelvin, by playing around with the bias current, I can operate the detector at 10 millikelvin or 20 millikelvin. The response will be very different, but I can still operate it.
Okay. So there's one question here by Vandana, but I would like you to take up very quickly 3 questions from YouTube. So then we'll ask Vandana, whose will be the last one. The question here, one is, actually they're just a couple of quick questions. These are slightly of different nature, but nevertheless, they must be answered. Sir, how these neutrino oscillations affect the ongoing measurements in the experiments? Like, as you said, they change their flavor.
Yes, so all this, so for say double beta decay, we measure the half-life. So measuring the half-life is fine. So double beta decay, neutrino's double beta decay, whether it will just tell us that whether it's a Majorana particle or not. Now, if I have to convert the rate or the half-life to say a mass of the neutrino, or try to figure out some what could be the masses of the neutrino, then we have to take into account all the parameters of neutrino oscillation in there, because they all come into the picture, and then they give me a combination which gives an effective Majorana mass. So when we have to translate it to the mass, then we do take into account all the oscillation parameters and putting the mass limit on the masses of the neutrino. And it's the same for single beta decay also.
Okay. Another question, of course, probably more straightforward. So what is the range of the low temperature here?
Okay, so the range of low temperature, what I have mostly talked about is 10 millikelvin to say 100 or 300 millikelvin. Most of the astronomy groups actually use, like they can operate their detectors at 300 millikelvin, depending on the size of the detector. So everything below 1K for sure.
Yeah. So that is the next question is actually follows up. This is from Ramchandran. How do you optimize the crystal size?
Yeah. So the crystal size optimization is again dependent on the application, how good of a resolution we want in the application. If we want to make a detector which will have an energy resolution of say 1 electron volt, then we cannot make it like this huge size crystals, because it will have a low heat capacity, high heat capacity, and you won't actually get the energy resolution required. So it all depends on the application and the physics that one looks for.
Yeah, thanks. So that brings us to the last question, which comes from Vandana. Yes, Vandana.
Yeah, so Vivek, very nice talk. That's the first thing. Then I have one comment based on Pilay's thing, and then I'll ask you a question. So, firstly, when you are now telling that for Cupid, you will go, your background will be improved by at least 2 orders of magnitude, right? That's what you are saying. From 10 minus 2, you go to 10 minus 4. Correct?
Yeah.
Yeah. So in that case, wouldn't the thermal neutron capture induced background in the germanium, copper, or your detector material be a problem?
So we have again done the simulations, and there's a neutron flux measurements at Gran Sasso, and using that, we haven't seen like it contributes, but it doesn't contribute substantially to the background. So at least not at the level that we are talking about.
So at the ambient underground background, it is not an issue.
Yes. Yeah, at least not something that we see in our simulations. Background simulations are.
So only
so the thing.
Go ahead.
So the thing is, like every time we operate these detectors, like Core, it gives us an information about the background that we can expect in that cryostat, right? So that's how we nail down our background model also. So it's not just Core, but different other experiments also tells us like what kind of background will be there.
So currently for the neutron or the muon in the core, currently for the neutron or muon induced background, which of the materials is the biggest hassle, copper or the tellurium?
It's for the neutron. It's for the neutron for core, I don't know. I don't remember actually. I should look that up.
No, just curious, just for neutron induced background. Maybe you can tell later. So now my real question was this. You have been now, because you gave a very comprehensive summary of all the low temperature detectors. So this is talking at 10 millikelvin, and we said that we have not yet reached, nobody has really achieved the real thermodynamic limit in terms of resolution. So there is a scope to do better in terms of improving. So do you think if one really goes to, I mean, what do you think in terms of the future, in terms of the next leap for these detectors, this technology? Do you think a microkelvin detectors will bring in something new, or just the larger size detectors with improving the resolution will be advanced?
Again, I'll just draw upon my experience in Core. And the problem is, if I look at the Core's energy resolution, it's actually been affected by the electronics and the vibration noise. Right? So unless we actually get rid of these noises, unless we can show that we are not affected by this, going down to microkelvin is not going to help us anyway. And also it depends on the like how do we sustain microkelvin temperature for n number of years. We don't have that technology yet. So dilution refrigerators are totally fine for running an experiment for long duration. We need some breakthrough in cooling also if you want to operate something at microkelvin.
So in that sense, you think the detectors have reached its limit of cooling?
Reached it.
Limit for cooling down?
Again, it depends on the observation time that we want. And I don't think, maybe it's limited by the dilation refrigerator. I mean,
Okay.
I don't see, I don't see an experiment which is supposed to run for 5 years using anything else but dilation refrigerator.
Okay. Yeah, so
that's great, Vivek. I think you took lots of questions, and it's really, I know, painful now. I think you have to sleep along with us and adjust for your 12 hours space clock or something.
Jet lag.
Jet lag. So, but nevertheless, thank you so much. I think it has been a great talk. The way you summarized so much of material, both in terms of the detectors, sensors, and also, talking about challenges that are there for future generation people. And so thank you very much. And we wish you all the best for all your R&D as well as your Core detector results in the coming months and years. With that, on behalf of all of us here and all the participants, we would like to thank you. And of course, continue to keep
Thanks for having me. Thanks for giving me the opportunity to give this talk.
Thank you.
Anyway, Vivek, good morning to you.
Thank you. I think the caffeine kicked in now.
Take care, Vivek. Okay.
All right. Thank you so much.
Thank you once again. For the rest of us, thank you and good night to all of you, and take care and stay safe.
Bye-bye.